Hey guys, welcome back to Module 6 and Module 7 review. We're just going to go ahead and get started. Hopefully this will help you with the quizzes if you have not taken them yet. I believe the Module 6 quiz is due tonight, and the Module 7 quiz is due on Wednesday. But if you're watching this video in the future, and this isn't the first semester I've used this video, then those dates will probably mean nothing to you, or those days will probably mean nothing to you. Anyways, this is really not a Module 6 review, it's more of a Module 7 review. The things in Module 6 I feel like are kind of a subset of Module 7. But yeah, so anyways, let's just go ahead and get started without any further ado here. Based on the standard normal probability distribution, we know that 95% of values are normally distributed of a normally distributed random variable are within how many standard deviations of the mean? Okay, so 95%. So this is just testing, hey, do you know how to use the table? That sort of thing. So let's go look at the table. All right. So if we want to know 95% of the values distributed between the mean, okay, then how do we, let's see how we're going to think about this, okay? I'm just going to draw one of these guys here. We've got some mythical mean here, and we've got some tails here, and we want to say that 95% is in here. Okay, so if we know that 95% of the values are distributed about the mean, then we know that 5% total are going to be on these tails. All right, so we can think about this as our confidence level. So we'll say 95% confidence level. All right, and that sort of implies that we have an alpha level of just 1 minus that, of 0.05. Okay, and so then each tail is going to be half of alpha. All right, so this tail is going to be 0.025, and this tail is going to be 0.025 as well. So we're just asking the question, okay, what is the z-value right here? Or what is the z-value right there? Okay, now knowing that this curve is symmetrical, knowing that it's a it's a bell curve that's symmetrical, we know that this z-value right here is just going to be the negative version of this z-value. All right, so let's go ahead and check that. So we're just going to look for the point at which 0.025 of the probability is to the left of a z-value, or 0.025 of the probability is to the right of a z-value. All right, so with our table, if we look on the left-hand side, we're going to be looking for 0.025. If we were to actually look on the right-hand side of the table, so the positive side of the table, we wouldn't be looking for 0.025. We would be looking for 0.975. Because if we want 0.025 of the probability to the right of a z-value, we'd need 97.5% of the probability to the left of it. So you'll see what I mean here in a second. Okay, so that's the logic here. So let's go look for 0.025 on this table. All right. So we've done this in earlier videos, but we've just never formalized it as an exercise. So going down until we see something, until we get past 0.025, boom, right there we did. We got past 0.025, we're at 0.0287. So then we walk over until we get to something really close to 0.025. Oh, lo and behold, we are at exactly 0.025. All right, what is our z-value? Negative 1.96. Okay, cool. Negative 1.96. So we get z equal to 1.96. All right, well, let's just check that. Let's check that on the other side. So if we wanted to use the top end of this, all right, we now have to look for the point where 0.025 of the probability is to the right of the z-value, which implies 0.975 of the probability would be to the left of it. So the number that we look for in the table is 0.975. Okay, so we start at the bottom here, or we could start, it doesn't matter where we start. Start here, getting to 0.97. Okay, we've just passed it, 0.9713. Going over, 0.975, we found it. Okay, so this is where 0.975 is to the left, or 0.025 is to the right. What is our z-value? 1.96. 1.96. So we can find it either way. It's always going to be easier to find it on the left side, because the number that you'll be looking for in the table, so the left side or the negative side, because the number that you'll be looking for in the table is the same number as your alpha half. Okay, so that's kind of an easy way, but you can find it either way. All right, so we're going to do similar things for 99%. So for 99%, we're going to be looking for, look for 0.005. For 98%, look for 0.01, and look for 0.05. All right, so we're going to work on the negative side. So we're looking for 0.005, passed it at 0.062, looking for 0.005, passed it, perfect. Negative 2.5, 8. And I think we just used that in a recent problem. Okay, I'll just put implies 2.58. We're just going to be using positive numbers here. All right, and now 98%, so we're going to be looking for 1%. Okay, start here, walking down 0.0107, passed it, and passed it here. 0.099, looks good. 2.33. And 0.05, walking down here. All right, we're going to pass it there, and then we get 1.65. 1.65. All right, so 1.96 is the z-value that is associated with the 95% confidence intervals. 2.58 is the z-value associated with the 99% confidence interval. 2.33 is the z-value associated with the 98% confidence interval, and 1.65 is the z-value associated with the 90% confidence interval. Okay, these numbers you kind of want to memorize, because for z-values, like, you're going to be using these all the time. You're just going to be using them all the time. Okay, for t, that's a little different. Your t values are going to change because they're going to change with how big your sample size is, your n is. But for these, like, you're going to see these 1.96, 2.58, 1.65 a lot. 2.33 probably less so, but the you'll see those. So get used to them. All right. Number 2, in an effort to estimate the mean amount spent per customer for dinner at a major Norca restaurant, data were collected for a sample of 49 customers over a 3-week period. Okay, so I'm just going to go ahead and write in n equal 49. Okay, just because. Assuming a population standard deviation of 2.5, what is the margin of error at 95% confidence? Okay. So, another thing we need to note, because we're not given any of this information, another thing we need to note is we have a population standard deviation. So that implies sigma is equal to 2.5. Okay, and then what is the margin of error at 95% confidence level? So we have CI is equal to 95%, which implies alpha is equal to 0.05. Okay. And so then it is asking us for a margin of error. So it's asking us for E. And because we have sigma, we know that we're in reference to our Z formula. So our formula, if you look back, is Z alpha half times sigma over the square root of it. Okay, do we have all these things? We have an n value, boom. We have a sigma, there you go. And the Z alpha half we can find. So let's see, alpha half is 0.025. Do we have something that is a Z value that is associated with 95% confidence level, or that is associated with 0.025? Yes, we do. and that would be our 1.96, 95% confidence level. So 1.96. So what is our margin of error? So we'll say E is equal to 1.96 times 2.5 over the square root of 49. And that is equal to roughly 70 cents. So 0.70. So that is our margin of error. If the sample size, for B, if the sample mean is $22.60, what is the 95% confidence interval for the population mean? Okay, so this is really, really easy because we already found the margin of error. So our confidence interval formula is going to be x bar plus or minus z alpha half times sigma over n, which z alpha half times sigma over n is the E that we just found, right? So this is just going to be our x bar plus or minus our E. So this is just going to be 22.6 plus or minus 0.70. Okay? And so then that just gives us an interval of 2190 to 2330. Okay? And then how does your answer for part B change if you use a 95% confidence interval? All right, instead of, 99% confidence interval instead of 95. Okay, so we write our formula down here. We have x bar plus or minus z alpha half times sigma over n. The only thing that we're going to be changing is our to reflect a 99% confidence interval. So z alpha half is going to be z alpha half or z of 0.005, which we know to be 2.58 because we just solved that in the last problem, right? So these are numbers that you are going to have to be familiar with. So then we get 22.60 plus or minus 2.58 times 2.5 over the square root of 49, or 7. And this just gives us a interval of 21.68 to 23.52. Okay, how does your answer for part B change if the sample size is 100 instead of 49? Okay, so we write down our formula again, z alpha half sigma over square root of n. I forgot to write that, square root of n. And so then basically we're going to use the z value that is in accordance for 95%. So that's going to still be our 1.96. So we just go ahead and plug in our formula, 22.60 plus or minus 1.96 times sigma, which is 2.50, divided by 100, square root of. Okay. And then we go ahead, and this is going to be 22.11 and 23.09. All right, so let's look at these. Let's kind of interpret what's going on here. All right, so let's interpret the difference between B and C here, okay? So in B, we have a 95% confidence interval, and then in C, we have a 99% confidence interval. What happens in the 99% confidence interval? The interval gets larger, right? We go from 21.9 to 23.30 in B. Now we expand outward, 21.68 to 23.52 in C. So in order for us to be 99% confident, in order for us to be more confident that our mean is in there, we have to expand the range. We have to expand the interval to say, okay, if we want to be really sure that the number's in here, we got to make the interval a little bit bigger. And that's what we're seeing mathematically here. Okay, now, so what's the difference between B and D? So in D, we up the sample size, okay? All right, so they're both 95% confidence. We have 95% confidence that our population mean is in both of these ranges. or is in both of these intervals. But for B, we only have a sample size of 49, and for D, we have a sample size of 100. What happens to the interval in D? Well, the interval in D gets tighter, right? So it shrinks, which means we have 95% confidence in a smaller interval, which is a good thing, right? Meaning we're more accurate. We have more precision, more accuracy with our confidence interval as it gets larger, or as n gets larger, which makes a lot of sense because if you look at the formula, as n gets larger, because it's on the bottom of the fraction, it's going to be making that whole margin of error term smaller, right? And then thus, the margin of error is going to vary much more smallly. It's going to vary much smaller with regards to x bar. Okay. Let me know if you have questions on that. Okay, because that's an important concept. Okay. So this is talking about point estimates. Okay, and this just has to do with recognizing that when we take sample statistics, they are in fact an estimate for something of a population. Okay, so what is the point estimate of a population mean for this sample data? Okay, so this sample data is a sample from a population, sample of quiz scores. Okay, so what's a point estimate for the population mean? So maybe this is just how many? 1, 2, 3, 4, 5, 6, 7, 8. So there's 8 data points here. So say this is a class of 100. Okay, but you don't have access to all 100 scores. So this is going to be our point estimate for the class average. So our x bar. And that's just going to be equal to add up all of these numbers and divide by n. Okay? And that is equal to, it ends up being 80 divided by 8, which is equal to 10. So 10 is the sample mean, which is like an estimate for the population mean. But we don't know how close that is. We don't know with any level of confidence. We just say, well, that's an estimate. Okay. So now we want to do, what is the point estimate for the population standard deviation? So the point estimate for the population standard deviation is the sample standard deviation. Okay. So the way that we calculate that is we vary each point from x bar, and we divide by n minus 1. So these are formulas that you guys have had and have already been tested on. So s squared is just going to equal the summation from x minus x bar squared all over n minus 1. Surely you remember that. We'll just say for all x. Okay. And so then let's run through this, I guess, these long calculations. And obviously s squared is the sample variance. We're going to take the square root of this whole thing to get our sample standard deviation. Okay, so we go ahead and we say 10 minus 10, because 10 is our first data point, squared, plus 8 minus 10 squared, plus 12 minus 10 squared, plus 15 minus 10 squared, plus 13 minus 10 squared, plus 11 minus 10 squared, plus 6 minus 10 squared, plus 5 minus 10 squared. This is going to be all over n minus 1. Okay, all over 8 minus 1. Okay, so what we end up getting when we run through all that math is we're going to get 84 divided by 7, which is equal to 12. Yes, 12. Okay, and that is equal to s squared. And so then, thus, s is equal to the square root of 12, which is 3.4641. Okay, so that is our population standard deviations point estimate. So it's our sample standard deviation. So now, what is the confidence interval for the population mean? Okay, are we going to be using Z or T? So we use Z when we have a sigma, and we use T when we don't have a sigma, when we only have an S. So because we only have an S here, we're going to be using our T. So we have the formula for a confidence interval is then going to be x bar plus or minus T alpha half, comma df, right, times S over the square root of n. Do we have an x bar? Yes. Do we have a T alpha half? No, but we have the components to find it. Do we have an S? Yes, we calculated that. And then do we have an N? We certainly do. Okay, so, and our X bar is 10. So we'll just write these down here. X bar is 10. S is equal to 3.4641. And N is equal to 8. So let's find our T statistics, so our T alpha half. So because this is a 95% confidence interval, our alpha is 0.05, and then thus our alpha half is 0.025. And then what is our degrees of freedom? Our degrees of freedom is equal to n minus 1. So df is equal to n minus 1 is equal to 8 minus 1 is equal to 7. So so that's that. So T of 0.025 comma 7, we look on our table for. Got to go to our T table. Go over to T of 0.025, which is right here, and then down to degrees of freedom 7, we get 2.365. All right, and then 10, I don't know why it is doing that. It's so weird. 10 plus or minus 2.365. Where is S? 3.4641 over the square root of 8. That is ultimately going to give us an interval. So 7.18 roughly, and 12.82 roughly. Okay, so this is the interval for which we have 95% confidence that our mean is in. Okay, so that is that, guys. Please let me know if you have questions. I know that this review is going to feel like I'm running through things, but yeah, sorry. No, in all honesty, the luxury of the review is that you can rewind, or the luxury of the video is that you can rewind it and rewatch it. So I'm not going to kind of overly spend time explaining things and re-explaining things and re-explaining things in the way that I would in a normal live classroom setting, just because you have the opportunity to go back and rewatch it and kind of answer the question like, wait, what was he doing there? Wait, why did he do that? So here's what, I mean, that's what I would want you to do, is rewatch it if you don't understand something, and then once you've rewatched it and still don't understand something, either rewatch it again or come ask me questions or ask a peer or look for another resource or whatever. But I want you guys to understand it, but I understand that it's going to maybe feel as though I'm moving through these things quickly. But I think that, I think that that's fair. Okay. All right. On to the next problem. All right. Next example in the review, the EPA City Highway MPG range for a Saturn Vue four-wheel drive automatic 5-speed transmission is 20 to 28 mpg. If you owned this vehicle, how large a sample, how many tanks of gas, would be required to estimate your mean mpg with an error of plus or minus 1 and 90% confidence? The standard deviation is assumed to be 2 mpg. All right, assumed. That's a very important word. This implies we're talking about a sigma, not an S. All right, so that's a 2, 90% confidence. Okay, or confidence level, CI or CL, whichever you want to view it as. That implies we have an alpha equal to 0.10 or an alpha half equal to 0.05. And then an error equal to 1. And then what else? So, because it's asking us how large a sample. So all we need to know is, we're finding an n. So n equals what? All right, so we have a formula for that. And we know what formula that we're using right off the rip. Okay, something I forgot to show you guys, which is on Brightspace, is the Unit 2 grid. Okay, so the Unit 2 grid is going to have all the formulas that you're going to need for the next test. Okay, this should be a decent tool to help you study. And this will be in the announcement that you would have just read. Okay, so the Unit 2 grid, so this has all the formulas and has all the names of all the everything. And yes, you will be able to use this on the next test. Sounds good? Sounds good. All right, so this kind of just takes all the formulas that we learned already in the videos and throws them all into a table, as well as there's some more formulas of topics that we haven't covered yet. Okay, so for our finding a sample size, we have n equals z alpha half times sigma divided by e, and then the whole thing squared. Yeah. All right, so we get out of there, we get back to the problem. So the formula that we're going to be using, given what we just looked at, or given you kind of like looking back at your packet, is equal to n equal to z alpha half. My pen is doing crazy things again. It is driving me up a wall. Times sigma over e. Gosh, that is killing me. Okay, anyways, that's our formula. And I'm getting text messages, so I am very sorry about that. So what we do is n equal z alpha half. So what is our z alpha half for a 90% confidence interval? It is 1.65. I'm not going to go back there and show you how I did it or anything like that. We just did that. Yep. And then what is our sigma? 2. And what is our margin of error? 1. And that whole thing is squared. So this comes to 3.3, whole thing squared, 10.89, which then whenever we're doing an n calculation, we always round up. So 11. That's the number that we need to have 90% confidence. Of 43 bank customers depositing a check, 18 received some cash back. Construct a 90% confidence interval for the true proportion of all depositors who ask for cash back. Gosh, it doesn't feel like enough information, but actually it is. Okay, so notice some keywords here that we have. We have proportion, right? So this automatically tells us the set of formulas that we're going to be using. We're going to be using our proportion formulas. Okay, so and that is our p hat plus or minus z alpha half times that big square root of p hat 1 minus p hat all over n. Cool? Cool. All right. And it also asks us to check for the normality assumption. So this can be something that, first of all, this is something that we didn't cover prior to the review, but we are going to cover it, and you may be asked questions on it. Note that it is on your grid sheet. Note that it's in the slides. And the normality assumption is just n times p hat and n times 1 minus p hat. Do these both answer the question, are they greater than or equal to 5? Okay, if they both answer that affirmatively, if the answer is yes for both of them, then the normality assumption checks out. Okay, that's that. Okay, so let's construct our 90% confidence interval. Do we have a p hat? Sorta, right? So we have an x value, which is 18, and then an n value, which is 43. And so we can make our p hat with x over n, 43, which is equal to 0.4186. Cool. All right, so we have a bunch of the components now. So we have an n, we have a p hat, we have another p hat, we have another p hat, and we just need to know our z alpha half. So z alpha half is just going to be your z of 0.05. And that is equal to what? 1.65. We know that from problems that we've just done. So let's create our confidence interval, 0.4186 plus or minus 1.65 times the square root of 0.4186. 1 minus that, which is going to be 0.5814, divided by n, which is 43. Okay, we run these numbers. And we get 0.294467, comma 0.54273. You don't need that many decimals, but I gave them to you anyways. And then we check the normality assumption. Our n is 43 times our p. And that is equal to what? That's equal to 18. And 43 times our 1 minus p, which is 0.5814, is equal to 25. These are both greater than 5, so our normality assumption checks out. All right, so on to the next thing. What sample size would be required to estimate the true proportion of American female business executives who prefer the title Miss with an error of plus or minus 0.025 and 98% confidence? Gosh, that is a weird question. I'm not going to take credit for making these questions, so do not assume that I made the questions. I got these from a instructor prior to me, okay? So yeah, I just kind of use some of the materials sometimes, and yeah, I forgot to edit this one. So anyways, not the most intelligent of questions, or I don't know. But anyways, we can use it as an example nonetheless. What sample size would be required to estimate the true proportion of American female business executives who prefer the title Miss with an error rate of 0.025, so that's our E, and 98% confidence, so confidence level is that, which implies an alpha level of 0.02, which implies an alpha half level of 0.01, and that's that. True proportion, it's talking about proportion. Okay, so we can use our proportion formula. P times 1 minus P times Z alpha half over E whole thing squared. All right, and we don't have a proportion here, so what do we use? We use 0.5 because that's going to maximize our N. This pen is killing me right now. 0.5 times 0.5 times the Z alpha half. Our Z alpha half of 0.01 is going to be 0.23. I'm going to have to fix this pen if it's going to keep doing this. 0.025 squared. I'm going to get through this slide and then, or I'm going to get through this problem and then fix the pen. But ultimately we're going to get 2171.56 or 2172. Yes, I gotta go fix this pen. So I'm gonna pause the video and it won't feel like any time has passed for you guys. Okay, and we're back. So when I go into older versions of Word, it usually ends up working better. So that's what we're gonna do. Alright, so the next problem, what sample size will be needed to estimate the true proportion, keyword, of students at your college who are wearing backpacks with 95% confidence, okay, 95% confidence level, and an error of plus or minus 0.04. Don't know why the formatting did that. So E is equal to 0.04. Okay, and so we're going to use similar formula. So N is equal to P times 1 minus P times Z alpha half divided by the error squared. So because we're not given a proportion here, we're going to just be using 0.05 times 0.05 times our 95% confidence interval Z, trivia, 1.96. Okay, and our error, which is 0.04, whole thing squared, it's going to give us what? 600.25, which is roughly 601. So that's that. And that's that. That is the whole video, guys. So please let me know if you have any questions. Sorry this is a more long-winded video, but you got to get through it for the review. All right, thanks so much.